functions are some of the most important functions in mathematics, and it can be used to model all sorts of different scenarios, from measuring population growth and population change, like for bacterium or a certain virus that's going around, all the way to the financial sector, such as interest from banks. Now let's focus on the financial side and talk about compound interest, which is historically where the number E, or Euler's constant, was first discovered. So say you rolled over to a bank that gives you 100% interest after 1 year if you give your money to them. And what this means is after 1 year, you get 100% of the money you put into the bank on top of the money you already had. So then you end up with double the money you originally had. Now let's say you roll over to another bank, but instead gives you 50% interest every 6 months. Now would it be better to put your money into this bank or the other bank? Well, let's calculate it. Say you had P amount of some currency. Then for a bank with 100% interest at the end of the year, we would end up with P plus P, which can be factorized as P times 1 plus 1, which is just 2P. Now for a bank that gives 50% interest every 6 months, we start with P, and then 6 months down the line, we get 1/2 P or 50% P more. And then 6 months after that, we end up with 50% of the amount that we already have added on top. Now this amount can be simplified and factorized to P 1 plus 1/2 all squared. And this is equal to 2.25 times P. So you see, we end up with more if we use the 50% twice rather than 100% interest once at the end of the year. Now, what about 33% interest every 1/3 of the year, or every 4 months? Well, we can do the same thing, and we see that at the end of the year, we end up with P times 1 plus 1/3 all cubed, which is equal to 2.37 times P. Now, we see that this value is getting larger and larger the more times we have interest imposed. Now, if we kept going, then we see that 100 over n% interest every 1/n of the year gives us a final value of P times 1 plus 1 over n to the power of n. And because it's getting larger and larger, we want to find the maximum value that it can be to get the most amount of money that we could get. So essentially, we want to know the limit as n approaches infinity of 1 plus 1 over n all to the power of n. And actually, we can calculate this number, and it ends up being this irrational number 2.71828 ... And this number is famously written as the letter E, similar to the way that we write 3.141 ... as being the number pi. And E is known as Euler's constant. And what this means is that the maximum amount that we could end up with is E times P, or 2.7-ish times P. Now, we see that as n approaches infinity, 1 over n approaches 0, and n in the exponent approaches infinity, of course. But if we make the substitution k equal to 1 over n, then k approaches 0 can replace n approaching infinity, and we get the limit as k approaches 0 of 1 plus k all to the power of 1 over k, and this is another more useful way of writing the number e. Let's now try to differentiate exponential functions. Say we had y equal to 2 to the x, then what is dy dx? Well, we remember that dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Now, if we take f of x equal to 2 to the power of x, then we have the limit as h approaches 0 of 2 to the x plus h minus 2 to the x all divided by h. Now, by an important rule of exponents, we can write 2 to the x plus h as 2 to the x times 2 to the h. Then factorizing in the numerator, we get 2 to the x times 2 to the h minus 1 all divided by h. Now, we can interchange 2 to the x and the limit, as 2 to the x has no dependence on h. Now, this limit we can actually calculate, and we get some irrational number 0.6931 ... Now, this value also has a symbol which we will see later, but for now let's call this constant k2. So dy dx is equal to 2 to the power of x times some constant k2. Now we can do the same for y equals 3 to the x, and we get dy dx is equal to 3 to the x times some other constant k3. And for 4 to the x we do the same thing, and we get dy dx is equal to 4 to the x times some constant k4. And we can keep going like this, and we see that if y is equal to a to the x, then dy dx is equal to a to the x times some constant k. Now this is great, we found what dy dx is for exponential functions, but each time we have to calculate this constant k from scratch. So can we make k equal to 1? That is, can we find a value a such that if y is equal to a to the x, then dy dx is also equal to a to the x? Well, we know that we can write dy dx as a limit, and we can then divide both sides by a to the x. And we see that this left side is actually our constant k from before. So we want our value k to be equal to 1. So now what value of a should we choose? Well, let's try a equal to e, Euler's constant, and we remember that e is equal to the limit as h approaches 0 of 1 plus h all to the power of 1 over h. Now we don't need to write the same limit twice, and we see that h cancels in the exponent. Then the 1's cancel in the numerator, leaving the limit as h approaches 0 of h over h. And we know that h over h is just 1, and since there are no h's left, we can remove the limit and we get 1. This means that if y is equal to e to the x, then dy dx is also equal to e to the x. And because the derivative is itself, this makes y equal e to the x one of the fastest growing functions in mathematics. And in fact, it's scarily quick, because this means the spread of infectious diseases is extremely fast and only gets faster. Now let's take a look at one of the slowest functions in mathematics, and it's very related to one of the fastest functions in mathematics, and that function is known as the natural logarithm. Now we know that 2 squared is equal to 4 and 2 cubed is equal to 8, but 2 to the power of what is equal to 6? Now we can write this number as log base 2 of 6, where log base 2 is a function, and to see how we get this function, let's consider y equal to log base 2 of x. Now we have a graph of y is equal to 2 to the x, and if we reflect this graph in the line y equals x, then we get the inverse function y equals log base 2 of x. Now let's replace 2 to the x with e to the x, and remember e is a number 2.71828 ... Then its reflection in y equals x becomes y equal to log base e of x. Now log base e of x is famously written as ln x, which stands for Logarithmus Naturalis, which is Latin for natural logarithm. Now logarithms have some very important properties, namely the logarithm of a product is the sum of logarithms, which also implies that ln of x to the k is equal to k ln x. And since exponentials and logarithms are inverse functions, then e to the ln x is equal to x. Now with this, we can also see that ln of x divided by y is equal to ln x minus ln y. Now, the natural logarithm is one of the most important functions in mathematics, and we can start to see its usefulness when we differentiate it. So take y equal to ln x, and we know that dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And substituting in, we get ln of x plus h minus ln x in the numerator, and now from one of the properties, we can rewrite the numerator as ln of x plus h divided by x. And let's write this divided by h to the side as 1 over h, and we know from another property that we can bring this 1 over h to the exponent. Now we see here that x cancels, which leaves us with 1 plus h over x. And similarly to before, let's make the substitution n equal to h over x. So first we change the limit as h approaches 0 to the limit as n approaches 0, because when h approaches 0, n also approaches 0. And then we have 1 plus n in the bracket and 1 over nx in the exponent. Now we can write 1 over nx as 1 over n times 1 over x, and by one of the logarithmic properties again, we can bring 1 over x to the front. Now we can swap the limit and natural logarithm, and we see that this part here is our number e. And since ln of e is equal to 1, we have that when y is equal to ln of x, dy dx is equal to 1 over x. And this unbelievable connection has very important consequences. For example, if any of you have done integration, then you know that you cannot calculate the integral of 1 over x dx the normal way. But here we show that this value is equal to ln of x. Now this relation also is the reason why the harmonic series, which is the sum of all 1 over n, diverges to infinity. And a very useful trick is that we can write a to the power of x as e to the ln of a to the x, which is just e to the x ln a. Then by the chain rule, we see that the derivative of a to the x is equal to a to the x times ln a. And this ln a is a constant k from before. So instead of calculating k from the limit, we now know what that constant should be. And this is the reason why we always see exponential functions written as e to the kx rather than a to the power of x. And as a real-life example, we can measure the radioactive decay or half-life of a radioactive substance. And what happens is over some period of time, the mass of the substance is halved, which gives a graph like y equals 1/2 to the power of x. Now we can rewrite this as y equal to ln of a half x, which is just e to the minus 0.693 ... x, and now we can do whatever we want with it. Now definitely make sure you get used to these functions and know them inside and out, as you will see them a lot throughout your mathematical journey. So if you liked the video, be sure to drop a like on it and hit that subscribe button if you want to learn, explore and master more mathematics. And head over to mathesy.com where you can find all my notes, my videos, and if you want to support the channel. Hope you guys have a good day, and I'll see you all next time.